Oh, this is probably the ZX Spectrum machine code lesson you don't really want, but you're going to get it anyway. I'm going to take you through the scroller machine code program from Sinclair User 44 and a slight adjustment I've made to it. But I'm going to take you through as best I can what everything does and how to read it. And hopefully at the end of it we both get a better understanding of what's going on, because I'm still a learner as well. Right, we're going to take you through it. Now on this page here, what I really want to talk about is the lower section, but to help us, what we're going to do in this example is, although it's not shown, we have got a top section, third of the screen, and what I've been doing here at home is I'm concentrating on the lower section of scrolling for my worms game and the like, because I want this area to be free. We just need to scroll landscape in the lower mid sections. So I've been mapping out the screen where it is for big blocky characters, getting onto ZX Paint and finding out what the actual memory locations are, because it tells you at the bottom of the screen, and every little pixel you get the address for each byte. I end up with a list and a chart. I want something to start at the Y and X coordinates is backwards for spectrum at number 16 down at X0. I want to start here, is what I'm telling it. And these are the memory addresses it's pointing to, and it's going to be a total size in bytes of that. All those big squares, in other words. And the same for the display file. It's how many pixels up on the screen you're starting from. Their address in the memory, this little dot here where it says start, right the way through to that endpoint there. So I'm going to manipulate that block only, is what I'm trying to set up. And it is 1.95K, 1952 bytes in size. So that, for a game, is what we're trying to achieve here with these scrolling programs. You can start letting your imagination run what you'd like to do with it, because by the end of this you'll be able to scroll individual lines, not big blocks like that. You'll be selective on what you want, which is exactly what we're after in games. Now let's get into assembly and machine code and how it differs from the ZX Spectrum Basic, which you know is typing in keywords that are easy to read, and when you run them, the machine magically converts them on the fly to machine code so it can read it and do what it wants, what you want it to do, sorry. And we all know that cripples the speed in the system massively, and you can't get the best of the machine. Though we're good programmers and we read from the best places to get the best techniques, it still isn't enough to do what we want. And we're going to have to rely on machine code to up the ante, to make better programs. Hybrids of a basic program and a machine code, like a scrolling program that takes a lot of weight out of the basic listing, because doing a scroll like this is a small amount of memory in bytes, the little routine we're coming to later, compared to a basic program. To get those 5 or 6 blocks to shift that way successfully and at speed is a programming nightmare. You do it in machine code and it's instantaneous, smooth, beautiful, like an arcade machine. And that's what we're chasing. So we need to learn some things about the ins and outs of programming and what we're going to be handling in terms of how do we handle numbers and load things in and make things happen. Well, like in the basic language, we can assign a variable and give it a number. You know this as let A equals 1, let B equal 2, whatever you want. In machine code, in the ZX Spectrum, on the Z80 CPU, we only have a handful of variables available to us. right? When you come to write your program on paper or on assembly, you can make a reference to it, what name it is, like let high score equal 2000. You can reference it in the assembly listing, but you can't actually write that into the machine code program, and you'll see why. In other words, we're taking the tokens out and we're writing to the machine directly. So we have registers. The ZX Spectrum has a set of registers, and these are the commonly used one: A, B, C, D, E, F, G, H. These are the ones I've seen. These are the ones that are generally used, and each little box is only a byte in size. It's an 8-bit register. 8 little bits per box. It can hold, each one can hold any number from 0 to 255 in it. And you can work upon them, increase them, decrease them, add them to something else, take them away, send them away for storage, or bring them back. Okay? Just in a similar manners that we'll do in BASIC, but just written slightly different. But because the ZX Spectrum's actually got 64K of memory, that's a big number. The total number of memory addresses in the ZX Spectrum 48 is 65,535 locations available. You've got the ROM above that and the display files, so you're actually getting about 27 to 32K to use yourself. Around about that. That's more than enough. But these registers can only count up to that number. They can't count up to that one. So how are we going to do it? Well, the electronics inside the Z80 CPU is going to do that for us. And we have commands that lump the two 8-bit registers together, which forms a 16-bit register, which can store numbers up to that value. Now, the other thing to note is that, yes, it lumps them together and treats it as one. And you can operate on each one of these as a pair at once. But you can also, at the same time, alter those individually just like you can with those. Okay? And you will see this happening later on. Selectively picking what you want as that value or that value, ignoring that one completely and just taking that one. All sorts of little things like that, and they all relate to the similar kind of things we're doing in BASIC, just written in a different way. So when you see double letters, they are two 8-bit registers joined to make a 16-bit one for numbers and memory addresses up to 65,535. Okay, let's go for it. Oh look, there's a doom gun. No, here's the hardcore stuff. Now I've taken line numbering out and the actual commands, numbers, the hex numbers that relate to these. We're just going to go through them and talk about them. We're breaking everything down into fragments, which are subroutines, and you can see I've blocked each one off. We start with a main script that makes a decision where you're going to jump to down the program, just like you would in BASIC. But what we're actually doing here when we use the command randomize user, now this here is the start of the program, and we're going to locate it at memory address 60,000. Okay, never mind the hex values just for now. Sorry, my writing's terrible, it's not supported. So when you say you randomize user 60,000, the program counter shoots down to here and starts executing that command, and it tells it. Now these abbreviations, we're going to load our variable box a register with number 1. The next thing we're going to do, so we've stored that number in the box, haven't we? The next thing we're going to do is like a go sub with a return. We want to jump down to the next that routine. Here it is. Okay, if you randomize user the next value. Oh, so what number is it? Well, if that's 60,000, that command, that's 60,001 for the number. And this will be 2 bytes, I dare say. No, this will be more because these are big memory addresses. So this is a 4-digit hex value that you know about. You know where you've stored that in the memory because it's X number of bytes down the list, as you're going to see. 60,000, that's address 60,000, 60,001, 60,002, 60,003, 60,004, 60,005, 60,006. Had a guess? No support. Let's just say it's that. So if you randomize user 60,006, you'll end up here. You'll call the right hand scroll, which just moves 1 block and comes back to you. Or if you've set it up as loops, it'll do as many as you tell it. So 60,006, 7, 8, 10, 11, 60,012 by writing. We'll bring up that routine to do the lower third of the screen. You can see, call that one for the top third, call that one for the mid third, call that one for the bottom, and get a return after each one instead of them running after each other. So just do that one, come back, just do that one, so on. You get it. Okay, so we're going to call number 1 just to do the top third. So we jump down to this fragment that says left, and we're comparing what's in the A register. Okay, and if they compare, you'll get this, they're both the same. If you're getting a null value, if you're not getting what you want, it'll jump down to the next one. Does it equal that value? Yes or no? It's a no, go to this one. It's a no, go to that one. If we're still not anywhere, you have to go back here and go, but we want to pick this one. So it compares up, we get to land here. And this is saying load. Remember, this is 2 8-bit registers joined together, and this is a commonly used one, HL. Load it with a memory address, okay, for the top third of the screen. That's the hex for the top third of the screen. And then we're going to jump down to left screen, which is down here. There it is. So left screen puts 64 into box B. We'll come to this in a minute. So it's just the same again. Which section are we moving and where we're going to jump to? The left scroll, the mid scroll, or a lower scroll. You make your selection. We're going to move 64 pixel lines worth. Big block. It says here that we're going to save these numbers onto the stack because we need them later on. We need to restore registers back to how we left them when we leave all of this. Otherwise, other programs will crash. Other fragments will crash if you do not keep a track on these things. Very important. Save your BC. It's like saying, let something else equal the values of BC and save them. Now we're going to reuse the BC register after we've put it on the stack. We can use it again. This is safe. We now load up BC with how many bytes per line across the screen do you want to pull over? We're going to add the previously saved value in HL, which was the screen address, and we're going to add the value of 32 to it. So it's like saying let HL equal HL plus BC. Then we're going to decrement it. We're going to decrement that one only. Remember I said, even though the as a 16-bit register. Viewed like that, we can also work on them individually, and that's what it's done there. It's using C as a counter. Okay? And it's only got 32 in it, which means it's only holding, C is only holding the value 32 because that's less than 255. So that's a counter. And there you go, it says it there. We're going to do it for 32 times. It's one less or something, you know, the maths. Because you are only going to move 31 lines because one of them is going to drop off the edge. But not in this one, because it's got a wraparound. Now here, this expression here where we are loading from the H, loading D with whatever's in H, loading E with whatever's in L, and decrementing E like another counter. And this here is the same as saying let DE equal HL minus 1. And once you've done that, got that, and you've operated on HL, save it. Going back to the A box, we're going to load the values that we've put here. Okay, now this is, because it's in brackets, it's relating to the address, not the actual value of the number. So these two combined are a memory address, which we're popping, sorry, it must be, it's a single value, it's 255. So I got that wrong, forgive me. It's taken something out of there. I can't remember that. I'm sorry about it. I've just cocked up on what that one does. Oh yes, sorry, I didn't put the note on. I've just remembered. This is saving the leftmost byte of the screen. Okay, because you've got X number of blocks you're going to shift. And this end one is going to disappear off the edge of the screen, isn't it? What are you going to do with it? Well, it saved the value of what it is, where it is, before it was moved. Then it's going to move it one block over, so it now appears off screen, disappeared, gone. But we saved it. So we're going to load the value back in and stick it over here. Because this block is shifted, we've now left with an empty space on the other edge of the screen. That's the blocks you want to shift. That's a space. This is going to put that value here. So it's a wraparound. Whatever disappears off that edge comes back on here and vice versa. You take these two lines out and that stops happening. Whatever we saved in HL and BC gets recovered. We're pushing onto the stack. Think of it like a pizza stack of numbers with the last in, first out arrangement strictly. So here we are, recovering HL and recovering BC to what we saved them in them before. Do a jump if it's not 0. Back to the start of L loop. It's a for next loop. So it jumps back to L loop and does all that again, saves the BC, does those operations as I've explained, not going through them again. When it's done, it's 31. Counts through, we've got to 0, we return back to the place we called it from. Go to the next program. There we go. Wow, oh my god, did that mess with your head or what? Probably. But I hope I've helped break it down so it doesn't appear so intimidating. And you can actually read it once you start doing things like this. And of course, each one of these things we've been looking at, these abbreviations, they all have numbers related to them that you find in the ZX Spectrum manual, Appendix 4. And you'll see all of these commands written down the center of the page and what numbers relate to them on the left hand side. both the decimal and the hex values. And if you're poking into them directly into memory addresses, you'll use the decimal values, whatever you're gonna put in, and those are commands that you've taken from the book and they relate to the program you've written. Or you get a hex loader and you might have there's a command, you'll actually type CD, which might be one of these, or you might CD and then there'll be OA, which could be load something, and so on, and put a value in 0030, and your little hex loader just reads it in pairs and puts them in the memory address that you've specified. You'll see this written called org, stands for origin, and that's your starting position. You're setting up finally to close this piece before you start loading up your lovely Spectrum with all this hard work. Don't forget to run a clear command for the memory. Otherwise this will go gobbledygook and all your basic program could just write right over the top of it. So the standard here is we always set this to one less than the place you want to start. 2009, which results in everything after that is available for your machine code program and won't be touched by anything else. So everything below that number, because we're going decreasing in value, is for your basic programs, and anything above that number is machine code, user defines and character sets. Right, there we go.